just going to check. I've got a couple of people missing. Just want to make sure that, you know, they are here. If they're here, I have actually marked them in. So Christopher, you're here now. Osman. Yes, you're here now as well. Zoe, not here. Tad, not here. And Chloe, not here. Okay, so I'm missing Chloe, Tad, Zoe, and that's it. Oh, Tad's just joined. Welcome, Tad. I'll mark the other guys in when they turn up. Okay, so first thing I want to do today is welcome a new student to our class. So we have a new student joining us today called Ali. I'd like to welcome him. Obviously, it can be quite tricky joining in the middle of online learning. So when we do go back to in-person learning, I just want you to make Ali feel as welcome as possible into our lovely class full of our lovely students. I know you're very caring. Okay, so yes, last class, I just kind of began a little overview of where we'd got to with the dynamics topic. So, but I didn't quite finish that. So what I want to do today is to get that completed. When I get that completed, I have a small assignment for you with 8 questions in it. They're just the examples that I have given you last class and this class is just kind of a combination of those type of questions. So I've posted all the notes already for you so that you can see the notes there, the assignments there as well for when we finish the synchronous part of this class today. Okay, so just going to kind of go through some of these, just the last bit, which was friction, and then just some practice questions, and then I'm going to hand it over to you to have a go at these, just a small number of practice questions, and then you can turn them into me through Classroom. If you have any difficulty turning in through Classroom, you can also bring it to me when I see you next, which will be on Monday in school. I did also as well just post in after I made the announcement about the exam not being this January. I posted that in as well just to confirm for you, just in case you ever needed to double check on that information, just so that you know where you are. It's always good to confirm these things. Right, so continuing with our dynamics review. Right, so the first thing, can you see my screen? Yes, you can. Oh my goodness. Please just excuse me for 1 second. I have a kitty meowing at the door. Okay. Right, so we have looked at friction. Okay, so there's 2 types of frictional force that we talked about. The static frictional force, which occurs when we have an object at rest and we need to overcome that amount of friction in order to get that object moving. And there's kinetic frictional force, which is friction that exists between 2 surfaces while an object is moving. Okay, so we have an equation here. We've got the frictional force is equal to a coefficient of friction multiplied by the normal force. Now the coefficient of friction, it's a ratio, so there's no units with this number because it's just a ratio. We can find the coefficient of friction experimentally. It's a property of the material. It's just basically a property of how much friction exists between the 2 surfaces. So it does depend on the material. Obviously, something like ice has a lot less friction than something like sandpaper. Okay. So I also showed you this graph previously. Hold on a moment. Can you see that? You can see that just now. It's very trying, this. I have to keep coming out of my presentation to make sure you can see the screen. Okay, so obviously we've seen this graph before. This graph just shows us that in order to overcome the static frictional force of a stationary object that we want to get moving, the static frictional force is always going to be higher than the kinetic frictional force. So this graph just shows this object, the amount of frictional force. As the object begins to move, the frictional force is really quite high. And then we've got the kinetic frictional force. Sorry, the static frictional force is quite high. And then we've got the kinetic frictional force as the object continues in its motion. So we did a little kind of in-class activity on this where we had these force meters. So we could read how many newtons. And we had blocks of wood with different surfaces on them. And we were just trying to see trying to read off what the static frictional force was and the kinetic frictional force at that time. Okay, and let's see. So I want to do some problems with you now. So I think you can see that problem. Okay, so I'm going to go back to my really high-tech pen and paper to help me with this. Right, so we did some example problems for force equals mass times acceleration last class, and also for gravity. So these are some examples of how to solve problems with friction. Right, so this question says, what is the force of friction acting on a 10 kilogram rubber block sliding along a concrete floor? The coefficient of friction is 0.65. Okay, so I always advise you to always begin with a free body diagram. So I will try and get these pictures uploaded onto the classroom as well. I know that I think was it Emily that asked me, but I will try and get those done for you. Okay, so the free body diagram. Okay, I've got my object in the middle, my concrete block, not my concrete block, my rubber block sliding along the floor. So I've got the force of friction, and the other forces that will be involved in this in this particular situation will be the force of the weight, which will be acceleration due to gravity multiplied by the mass of the block, and the normal force, which is acting in an equal and an opposite direction. So I know that the normal force is going to be equal to the weight here, because the object is neither sinking into the ground nor floating in the sky. It's just resting on the surface. So right, so sorry. So here is my equation. My force of friction is equal to my coefficient times my normal force. So there's my equation there that I'm going to be using for this. I've got a tab in the way, I can't see what I'm showing you. There we go. So my force of friction. So I know what my coefficient was because that was given to me in the question. So that is 0.65, and that doesn't have any units. And I know what my normal force is going to be because that's equal and opposite to the force of the weight. So my force of there we go. So I've got my coefficient of friction there, and I've multiplied it by mass multiplied by acceleration due to gravity, which gives me my weight in newtons. So if I work that through, just put that into my calculator, then I should end up with that answer. Okay, so that's an example for that first question. Right, so let's have a look at another problem. Okay, a 1 kilogram hockey puck slides across a frozen lake with a frictional force of 36 newtons. What is the coefficient of friction between the puck and the ice? Okay. Let me just get back to my screen where I can see you guys. Right, so again, I'm going to start with drawing a free body diagram. Someone asked me a question. Let me look in the chat, see. Oh, I'm sorry, I didn't see the question. Okay. The cat's name is Safi. Hold on a second. I'm sorry, I didn't mean to ignore your question. So this is Safi. So Safi, come and say hello to my physics class. She's going to walk all over my computer now. There we go. I'm sorry about that. I missed that in the chat. She's actually only a kitten. She's just about 6 months old. And she's into everything. So there we go. Don't know if it can. There you go. Off you go. Right. So she's no good at helping me with these problems, though. There. Okay, Ishman, what's your question?
So do we use 9.8 or negative 9.8?
Right, that's a really good question, and I'm glad you asked that. So obviously, it would be for the force, for the weight, it would be negative 9.8. But because my normal force is going in the opposite direction, I've used the positive 9.8 there because the normal force is acting in the opposite direction to the weight.
Okay.
Okay, thanks. Sorry, I didn't have my chat open when I was... That's my bad. Okay, right, so the next question. Let's start the next question again. A 1 kilogram ice hockey puck slides across a frozen lake with a frictional force of 36 newtons. What is the coefficient of friction between the puck and the ice? So I was just beginning to draw my free body diagram to help me with this question. Okay, so there's my free body diagram. Okay, so again, I'm going to use my equation. My force of friction is equal to my coefficient multiplied by my normal force. Now, so there's my equation that I've written out, same as last time. So again, my ice hockey puck is neither sinking into the ground nor floating in the air. So the normal force will be equal and opposite to the force of the weight of the hockey puck. So this time I'm trying to find out what the coefficient is rather than what the frictional force is. I know what the frictional force is. So I need to rearrange my equation to be able to solve that. So let's just do that. Let's just rearrange that equation. So I've rearranged that equation. Okay. So, and working that through, so we know what the frictional force is, that's 36 newtons. And we know that the normal force is equal and opposite to the force of the weight, and weight is mass times gravity due to acceleration. So we've got 1 kilogram multiplied by 9.8 meters per second squared. So when I work it all out, that's what I will get. So the weight of my, sorry, I'm just trying to get that in the window there. The weight of my hockey puck is 1 kilogram. And acceleration due to gravity is 9.8 meters per second squared. Because this is the normal force, it's upwards. So that's a positive value for that rather than a negative value because we're not going downwards. And that gives me a 3.67, which is my ratio. And that's my coefficient of friction. Okay. Does anyone need that up for any more time? Right, so I have another problem here. It might seem a bit more complex, but we really solve this in the same way. So I'm just going to take another fresh page. Oh, what are you doing here? I can't get to my pages now. Oh, man. You're just getting in the way, aren't you? There. Right, so this is the next question. So a car of mass 1.2 tons is traveling along a straight horizontal road at a velocity of 20 meters per second when the car brakes sharply and then skids and friction brings the car to a rest. If the coefficient between the tires and the road is 0.8, calculate the friction of the car tires on the road. Okay, so there's a bit more in this one. Okay, I'm going to start again with my free body diagram. So I should have drawn that along the arrow. Let me just... Okay, so I've got my free body diagram there. So as the car was moving, there was an applied force from the engine causing the car to move. But the car is slowing down, skidding to a stop. So my force of friction is much larger than my applied force, which was causing the car to be traveling in a constant motion beforehand. I also have the force of the weight of the car, and I have the normal force as well included on my diagram. And I've put the mass in the middle, just to be helpful there. What are you doing? Okay, so we need to calculate the friction of the car tires on the road. So we need, first of all, in order to calculate friction, the force of friction is equal to the coefficient multiplied by the normal force. So that's our equation that we know about already. So we just need to calculate our normal force. So our normal force is equal and opposite to the force of our weights. Okay, so force normal is 1200 kilograms multiplied by 9.8 meters per second squared. So my normal force is therefore going to be 11760 Newton. So I've calculated my normal force there, because it's going to be equal and opposite to the force of my weight. So then my force of friction is going to be equal to 0.8, which is our coefficient of friction, multiplied by the normal force that we have. The normal force that we've calculated and I'll just pop the answer in there that I got. So the force of friction is equal to 9408 newtons. There we go. Okay, so then there's a second part to this, which I've included on the next slide. And it's the same question, the same information, but then the second part of the question at the kind of end of this says, calculate the deceleration of the car. Okay, so we can do that. We can do that using our equation of force is equal to mass times acceleration. Okay, and if we rearrange that, then we get acceleration is force divided by mass. Wait. I'm going to eat these instead. Right, so we already know what the force is, the net force, because we've worked that out. And we know what the mass is. So 9408 newtons divided by the mass gives us the deceleration of the car. As it slows down and skids to a stop. Okay, so that really reviews the work that we've done on friction. So these are our general. What are you doing? Come on, get down. These are our general forces equations that we're going to be using. So we have these already, and on the question sheet that I've given you today, I've included these equations. I'll always provide these to you. Okay. Let me just do some 3 last problems before I let you have a go on your own problems. Right, so here's another problem to solve. A friend pushes a 600-gram textbook along a lab bench at a constant velocity with a 3.5 newtons of force. What is the normal force supporting the book? Okay, so start off again by drawing my free body diagram. 0.6. So in the question, it tells me I've got a 600-gram textbook. Now, we know that we need to work in kilograms, meters, and seconds for our units. So I've converted my my 600 grams into 0.6 kilograms. Now, the textbook neither sinks into the lab bench nor floats in the air. So we know that the force of its weight and the normal force are going to be equal and opposite. And we're told in the question that the lab book is pushed along the bench with a constant velocity of 3.5 newtons. Zero newtons. So what is the normal force applied to the book? So we just would like to figure out what the normal force is applied to the book. Well, the normal force is going to be equal to the force of the weight because they're equal and opposites. So it's equal to the force of the weight. And force of weight equals mg. So the normal force is equal to the weight, and we know that weight is equal to mass times gravity. So just putting the information in that we've got. We know the mass, 0.6 kilograms, and we know acceleration due to gravity. But obviously, because it's a normal force, it's in the opposite direction, so it's a positive value for that. So the force of our weight is going to be equal to the force of our normal force is going to be equal to 5.88 newtons. There we go. Okay, so that is, oh my goodness, what have I got going on up there? I don't want to print that. Cancel that. So let's have a look at another problem. Okay. All right, so that's right. So carrying on with the same kind of information as on the last one. So still we've got the 600-gram textbook being pushed along the bench with a velocity of 3.5 newtons. This time, the question is asking us to calculate the coefficient of friction for this. So to calculate the coefficient of friction, so we're going to be using that equation. We already have a lot of the information we need from the last question. But I do need to rearrange that equation to be able to solve this. So I've rearranged that and put the numbers in. I don't know if you can see that there. So obviously the answer that we worked out from the previous part to that question we need for this part. And then I get the answer. 0.59, that's my coefficient of friction. Because it's a coefficient or a ratio, it doesn't actually have any units. Okay, so because this is the same information as the last question, let me just redraw that. So 0.6 kilograms. So I'm just going to add in the extra information that we have now. So we know that the normal force is equal to 5.88 newtons, and we know that the force is equal to negative 0.588 newtons. Yep. And the applied force is 3.50 newtons. We were given that in the question. And because it's moving at constant velocity, the friction is going to be equal. Right, I don't know. Hold on, let me get that in there. So there's my free body diagram for that. So in the last question, we calculated the weights and the normal force. Now, because the book is moving at constant velocity along the lab bench, okay, so the forward force is going to be equal to the frictional force. You're so welcome, Leo.
Hi, Miss. I'm here.
Oh, hi, Chloe. Okay. Have you only just joined us, Chloe?
Pardon?
Did you only just join, or have you been there all the time?
Yeah. I'm here, but I just joined.
Okay. Well, I'm gonna put you in, Chloe. I've just kind of finished. I'm gonna pop you in late, if that's okay, because I've just finished kind of going through. Well, I have just got one last question to do as an example. So still with the same 600-gram textbook being going along the bench at constant velocity. The last and final question is, so seeing as we worked out the coefficient of friction there, which coefficient did we work out? Was it the coefficient for static friction or the coefficient for kinetic friction? So static friction, remember, is the amount of force required to get an object moving that is stationary, and kinetic friction is the friction that exists while an object is in motion. So there's no math for this one. It's just, which one have we worked out?
Is it kinetic?
It is kinetic. Thank you, Joshua. You are so right. Because we're told in the question that the textbook is moving with a constant velocity. So it is already moving. So the friction that we've worked out is for the textbook that's already moving. So good answer. Thank you. Right. So there are some questions for you to have a go at. I really would like to collect those questions in once you do them. So you can just do them on, normal paper, and then just if you can, I don't know, photograph them or somehow upload them. If you're not able to upload them and turn them into me that way, I can collect them from you in paper on Monday. I've put Monday for the due date, Ishmael, because just in case anyone has problems uploading it. But if you can get them in before Monday, that's all the better. Okay. Oh, my goodness. I think the kitten is trying to play the drums. I'm going to have to throw her out of this room. Yeah, we've got a drum set up the corner. Okay. Anyone have any questions? So you obviously, the questions that I've provided are just basically a mix of questions from Monday's class and today's class, just reviewing the work that we did Monday and today, which is what we've done anyway. So they should be quite doable for you. If you have any problems with it, I'm going to be here. You don't need to stay online while you're doing them. You can leave if you want to. Or you can stay if you want to.
So are we dismissed and then we can just do the work on our own time? Okay, yes. Thank you.
So the way that these online lessons run is half of the lesson is like teaching time, and then the other half is like self-directed time for you to complete a task. So
okay, that's perfect.
You're welcome. Thank you, Chloe. Miss. Bye. Thank you.
Thank you, Miss Richards. Have a good one.
You're so welcome. Thank you, Tad.
Thank you.
Thank you. Thank you, Carter.
Thanks, Miss.
Thanks, Miss Richards.
Thank you. Thank you, Joshua. Thank you, Alistair. Thank you, Christopher.
Thank you, Miss Richards.
Thank you, Joshua. So, Jane, you've got a question?
Yeah, for the second question there, it says draw a free body diagram showing the forces acting on a plastic rocket sitting in a launch pipe. But yes. I don't really know what a launch pipe is or what that would look like.
Okay, it's just a tube that the rocket would be launched out of.
Okay, and it's just sitting inside of it, it's not...
It's not moving. That's the key thing. It's just sitting inside the tube. So remember that you don't need to draw the launch pipe. You just need to draw a rectangle to represent the object. So it's actually much easier than, and it's just sitting there.
Okay, thank you.
Okay.